All right. Hey, everybody. Dave Limburg in Hong Kong with another episode of the THD Podcast. Joining us today, we have a company from Sweden. They're into Thin-ply Carbon for application in speaker diaphragms. So it's a company called Composite Sound. We're going to be joined by their head of Thin-ply Carbon diaphragms, Mr. Martin Turesson. So we're going to find out if I've got my summary correct, or hopefully we're going to learn a whole lot more about that. But without delay, we'd like to remind everybody to take a look at our sponsor. See if I get this right. The Alti organization, they'll be right here. We'll put up their logo and the link. During these crazy COVID times, we encourage people to reach out to Alti and find out how their organization and the networking that they can help further your business within the audio industry. So let's get to it then. So, of course, joining us, our co-host from Japan, Mr. Simon Weston. Hello, Simon.
Hi, Dave. How are you?
I'm very good. Thank you. And here we are, Mr. Martin Turesson, joining us from Sweden. How are you today, Martin?
Very well, thank you. How are you?
I'm doing well, thank you. And
Excellent.
Thank you for joining us. We've been talking about finding out about composite sound for quite some time now. And the company has evolved to become perhaps a specialist division of a larger company, but perhaps tell us a bit about yourself and a bit about how composite sound has come to be.
Sure. I think I'll start from quite far behind in time. So now Composite Sound, we're specialized in, we're developing and producing speaker cones, Thin-ply Carbon diaphragms. But it actually all started some 20 years ago when Oxeon was formed. That's our mother company. And Oxeon is really a materials company. Was started based on an invention to produce a new type of carbon fiber fabrics that enables considerably lighter, thinner, and stiffer composite parts. And the first customers to commercially use Techstream, which is the brand name of those carbon fiber fabrics, were the Formula One teams, because they could see that from one race to the next, they could reduce the weight of their composite parts. And today, an important part of Oxeon and Techstream is, Formula One, space, aerospace, focusing on ultralight, stiff solutions. And around 6 years ago, we thought that, hey, wouldn't speaker cones benefit from what we are good at, which is ultralight, stiff, optimized material solutions? So I started reaching out to the speaker industry, said, we have these solutions. I don't know enough about your requirements. Would you be interested in having a discussion about it? And people were interested in very open, and I spoke to a lot of people, and the more I spoke to people, the more I felt we have something quite interesting here. And the people I spoke to felt the same way. So that led to a number of just pilot projects, development projects. And quite quickly we saw, and our customers saw that, we can actually achieve a performance level which is far beyond what they had before. Actually, a true story, the very first samples we made for premium sound solutions in Belgium.
Yeah.
And usually when they test new cones, some of the audio team, they think it sounds better, others don't like it, and this was the first time they said that everybody in the audio team that listened to it said it enabled a considerable increase in sound quality. So that led to more and more development projects, and around 1.5 years ago we started producing speaker cones on a commercial level.
Okay.
And then we felt that we have really proven this commercially and technically, and we said, okay, it's time to accelerate this. And then it was decided to start a new company, and that was officially launched now 1.5 months ago, and that is Composite Sound. So Composite Sound is a spin-off from Oxeon, dedicated to the development and production of of speaker cones of Thinply Carbon diaphragm type. And I can also mention that when we already before we had composite sound, we wanted to promote the technology and explain what it is about, and it was nothing really like it in the industry, and that's why we created the category or the type Thinply Carbon diaphragms.
Mm-hmm.
So we are the creator of that category, and now we are building speaker cones, but under Composite Sound company and brand.
Okay. All right. Very good. Maybe just to visualize this discussion, you have a presentation to walk us through the details. Okay. Let's look at that.
Sure. So Composite Sound, our guideline, what we work for is that everything we do is about enabling you to make it sound like you want it to sound. And what do we exactly mean by that? Well, I will spend the rest of the presentation actually to explain that, but to summarize a little bit, loudspeaker design or transducer design is so much about making compromises. And a lot of those compromises come from limitations in the speaker cones and diaphragms. Basically, the speaker cone is not able to correctly transform that electromagnetic signal to sound waves. And a lot of that is due to an inability to control resonances. So our belief is that the key is to control resonances. And by properly engineering the cones and diaphragms and control the resonances, we can achieve performance levels that are far beyond what we can achieve if we would only rely on the material properties alone.
Okay.
And we use that technology then to engineer and manufacture Thinply Carbon speaker cones and diaphragms. But what's really cool about that is that same technology can also be used to engineer other components in which you want to control resonances or vibrations, and where you have also other requirements for ultra lightweight or great mechanical properties. I mean, the first that comes to mind is the closest parts to the speaker cone, the former, for instance. Mm-hmm. But it could also be surrounds, spiders, headphone cups, cabinets. Could also benefit from that same. So, by the way, I personally, when I look at a presentation, I think it's much more fun, if people ask questions rather than I just having a monologue. So please feel free anytime to ask questions or interrupt.
Yeah, I was just going to wait if you're going to get into it. But in terms of controlling the resonance, as I understand it, you're actually able to take the Thin-ply and adjust the weave, so to speak, to control perhaps the tightness of the weave and control those resonant at certain points within the diaphragm. Or am I understanding that correctly?
I will get into that at a later slide, but basically it's about anytime you vary the thickness or the stiffness in a given point, you will vary or influence the modal behavior. Mm-hmm. So it's really about optimizing thickness in different parts of the diaphragm, stiffness in different parts of the diaphragms, stiffness in different directions in different parts of the diaphragms.
Right.
By doing that, we don't just influence the modal behavior, we can actually optimize it.
Okay.
So I'll show that in more detail how we do it.
Okay.
But we are really born out of space and Formula One technology. As I mentioned before, we are a spin-off from Oxyon, and Oxyon's extreme Thinply Carbon materials are used in applications that have the absolute highest requirements on mechanical performance, ultra lightweight, durability. Here you can see a couple of examples. This is a Red Bull Formula One car. I don't know if you can see that, but you can see that distinct checkerboard textreme pattern here. This second picture, that's the NASA's drone that's up flying on planet Mars now, that uses, you can see it extreme in the rotor blades, and actually most of what you see here is built out of extreme materials.
Wow.
So we really build on the great material possibilities and engineering and know-how that Oxygen has built over the years, and add, say, acoustic know-how and to engineer composite sound Thinply Carbon diaphragms.
Yeah, I think that's just for people watching, it's a common theme that a lot of these materials for aerospace are also become the ultimate materials for speaker diaphragms, as kind of like the Webster's definition is of a diaphragm should be light as a feather and strong as steel. So the product requirements for both aerospace and Formula One racing and speaker cones end up being the same, similar materials a lot of the time.
Right. So
when you say thin ply as opposed to thick ply, what is thin ply? How do you define that?
it's actually a conventional carbon fiber fabric is woven basically from round yarns.
Mm-hmm.
But what Oxygen and Extreme does is take that yarn and I do like that, spread it into very, very thin tape. And then that tape is woven into a fabric. And each layer or each ply is extremely thin. So that's where Thinply Carbon comes from.
Right.
And by producing a carbon fiber fabric in that way, you achieve very, very different properties compared to conventional carbon fiber fabric. As I mentioned, you can make them much thinner, you can make them much stiffer, and you can also really optimize the properties to much greater degree. And I will also show that how that enables us to really engineer speaker tones in the way you want.
Okay.
What you were into there, Dave, about the ideal speaker cone, I think most people would agree, or as you say, the Webster definition is that the ideal speaker cone should be as stiff as possible, as light as possible, or as low density as possible, and it should be well damped. The problem is if you're trying to achieve that while only relying on material properties, that is basically impossible, because these physical properties or parameters are basically incompatible. A material that is very stiff is usually also quite dense and also quite poorly damped. And that leads to compromises. Typically, if you look on loudspeakers today, you have two philosophies or almost religions. You have the soft cone people and you have the hard cone people. So you're either forced to go for damping, like in a soft cone, paper, plastic, aramid type of cone, or you go for stiffness in a hard cone, aluminum, titanium, beryllium, even diamond. That's the pinnacle of a hard cone. And the problem is that by doing that, you are really making sacrifices. And our approach is to remove those limitations so that you don't have to make those compromises, that you don't have to make those sacrifices. So our approach is actually to enable you or the loudspeaker designer to combine high stiffness, low mass, and still have a well-damped controlled behavior. And we achieve that by not only relying on the material's internal loss factor. We use, let's say, a wider concept. We can call it resonance control. So the first step in getting a well-damped, you can call it well-controlled diaphragm behavior, is to engineer the modal behavior so that the modes or resonances we get are small amplitude to start with. And then in the next step, we use the material's internal loss factor, just like any other speaker cone technology. But then we have a much smaller resonance to dampen to start with. So that's, let's say, the basic idea and concept behind our cone technology. And that really enables us to combine a high stiffness, a low density, a low weight, and that's a good, let's call it a damping resonance control if we bundle that up. Okay. And the way we do that is what we mentioned also a little bit before, is that anytime we vary the thickness or the stiffness in a specific point, in any given point of the diaphragm, we will influence the modal behavior. So in a composite sound cone, so let's say in a conventional cone like this, in any given point, we can vary the thickness, the stiffness, but also the stiffness in different directions in different places. Mm-hmm. We can actually also vary the damping. So by optimizing these properties, we can then tailor the modal behavior. And if we look at a flat high aspect ratio diaphragm, for instance, that can be to maximize stiffness in one direction. We can actually sort of take stiffness from one direction and add it to another direction. Same with damping. We can maximize damping in one direction and minimize it in the other. And that really opens up for much more optimized, let's say, transducer solutions, motor structures, how you would, design the voice coil, for instance.
So it's almost like a structural cantilever happening within the construction. In the
very
weave.
much so. It's like I made the analogy to building a bridge. That imagine that you are building a bridge and you're only allowed to use one material that has the same properties in all directions, the same thickness in all directions, and that bridge should withstand, vibrations from cars and trucks, from winds, even from earthquakes. The requirements on a speaker cone is actually not that different. So you can imagine actually how limited you are in designing or engineering a optimized speaker cone if you are only allowed to use a sheet of material that has the same thickness all over, the same thickness all over. So that is, we are really, building a bridge, but it's a speaker cone. It's the same principles, really.
Yeah, and in so many of the materials used in a lot of speaker cones, there's no guarantee on consistency, or the tolerances are quite large.
Right.
Let's put it that way.
Yes. And so that's absolutely an important part as well. Like when we make these, we call them layups. So we can make the same cone basically in 50 or 500 or even 5,000 different ways that each will have a different modal behavior and a different frequency response curve, basically. When designing those layups, it's also to do it based on, design for manufacturing, but also for robustness, so that we can actually produce the cone in the same way, so that we get the same tolerances, or that we can stick within tolerance. So the frequency response curve and behavior is the same from cone to cone. So that's very important, yes.
This concept of manipulating the material properties in different directions, stiffness, damping, and so on, was that part of the concept when you first started making speaker cones, or did that come as a realization a bit later on after having made some?
That's a very good question. And that actually came as during the way when we start looking into how can we optimize the cones. We realized that a cone doesn't have the same requirements everywhere. We realized that by placing stiffness in different places will enable us. I mean, first it was more about, how can we make the cone as light as possible and push that breakup as high as possible.
Yep.
So we worked, to achieve that. And when we did that, we saw that these changes also influence the modal behavior very much. And we saw when we had these development projects with customers, and we sent them like 10 different cones of the same type, where we had then made sort of different stiffness profiles, that we got very, very big differences in the frequency response curve, for instance. So that was really, that led to what I'm going to explain more about this engineered cones. Mm. What really enables us to engineer the cones is the extreme Thinply Carbon materials. As I said before, the cones are not extreme cones. The cones are composite sound cones. They are the result of engineering, but the extreme materials are really the enabler for that. Mm. And extreme Thinply Carbon materials have some features that make them a great enabler for engineering speaker cones. One, they enable extremely high stiffness. And perhaps even more importantly, we can optimize the stiffness in different directions. Mm-hmm. Two, it enables ultralight weight, since, it's in the name, like you asked Simon before, Thin-ply carbon. Each layer or each ply is extremely thin, which enables us to stack, multiple layers of materials in different directions, in different places, and while still maintaining a low thickness, a low weight. Third is that we actually have a built-in damping mechanism called constrained layer damping. And this is not something that we came up with. That's a general method to control the vibrations. And in our world, we use it. So we have the very stiff Thinply Carbon layers, mm-hmm. One on top of the other. And in between each layer, we have a thin layer of special resin. Mm-hmm. And what happens in that when that laminate vibrates or bends, that special resin layer that expands or
contracts.
Yeah, contracts. Yes. So in that process, you get a lot of friction. So vibration energy is really turned into heat. Mm-hmm. And that was also one of the first, concerns we had before we made the first samples, that, conventional carbon fiber cones are not really known to be well damped. And here we are coming and making a considerably stiffer cone using much, much stiffer fibers. And we were fairly confident that, we could simulate the stiffness and the speed of sound and everything like that. But we had no idea about the damping. Mm-hmm. But it turned out that even if we make the cone in the same type of construction that would be made using a conventional carbon fiber cone, our cones are better damped. And that's due to this constrained layer damping. So this is really our first tool to achieve a well-damped controlled diaphragm behavior. And that's sort of a built in the material, you could say.
And is that special resin? Is that a secret sauce that you guys, through probably a lot of research or trial and error, or how did that come to be? Or is that something you can share?
There is actually a secret sauce within it. Let's say a large part of that resin is no, secret sauce. That's a standard resin, but we actually add a standard sauce that sort of creates some viscoelastic properties in that resin.
Okay.
We want to be as transparent with most things because we believe that's the best way to inform people. But there are some details that we like to keep.
That's fair.
So, and this second tool that we use to control the diaphragm behavior, get a well-controlled behavior, is actually in a way also, let's say, due to the materials themselves, and that's the concept of distributed breakup. If we look at a conventional speaker cone, can you see my pointer, by the way?
Sure can.
Yeah.
Good. A conventional, let's say, an aluminum diaphragm could be a paper or a polypropylene. It's what's called isotropic, meaning it has the same properties in all directions, and the driver is typically also, axis symmetric. So what happens is that you get these symmetric big round breakup modes. So you have big areas of the cone moving in and out of sync at certain frequencies, causing big variations in the sound pressure level. And you can see that in the frequency response as these peaks and dips. In a composite sound Thinply Carbon diaphragm, we get then what we call distributed breakup. And that's due to we have different levels of stiffness in different directions. So we break that symmetry and eliminate those symmetric breakup modes. And those are replaced with local, smaller, distributed breakup modes. And each of those modes have a much smaller effect on the sound pressure level. So if we look at that schematically, we, instead of having these big peaks and dips, we get smaller, almost like ripples. And typically what we're doing is we're sort of eliminating that first big breakup mode. And then by basically having a higher stiffness to density ratio than most materials, we can also push those resonances higher up in frequency. Typically, we can also reduce the mass, so we get a higher sensitivity.
And just so the distributed modes, like historically, like a distributed mode loudspeaker always had great off-axis sound pressure level. So does your material echo that kind of features as like versus a traditional, which might be more directional?
I would say that this is an extremely interesting area that we're actually actively, let's say, researching right now. And I wouldn't put it like we get a wider directivity or that we get a smaller directivity. What we can see is that by, let's say, engineering the modal behavior in different ways, we can influence that off-axis behavior. So we can actually, in a way, influence that level of directivity. Okay. But I wouldn't say that we have like a, fixed method, or that we can say we do it in this way and we get a wide directivity. We're not there yet, but I'm sure we will be there. We are at a level where we see that it definitely varies depending on how we do the modal behavior.
Yeah. Okay. It's something I noticed, like perhaps better definition with your Thin-ply weave, but I think throughout composite cones there is this kind of thing I can never quite figure out, is how they create that kind of instrumentation and better off-axis with these woven materials. It's just something I can't put my thumb on as to what's creating it and studying it.
Right. I mean, that's sort of what we want to do. It's like we don't want to leave it up to, let's say, the cone. Usually say the cone material. If you're using aluminum, you get one kind of, let's say, behavior. If you're using paper, another, and if you're using aramid, a third.
Mm-hmm.
I mean, of course, the material that we use gives it a certain timbre, but our approach is to be able to actually engineer that behavior.
Mm-hmm.
It's not just like it's an effect of the material. We use the material when you engineer it in different ways to achieve different behaviors.
Right. Okay.
So this, let's say, what I've explained up until now has been, I would say, very successfully used in a number of applications. Here are some examples. Here you have SP Acoustics, their Satori line.
Mm-hmm.
This is Ex Machina, their smallest studio monitor, the Pulsar. You can see the composite sound Thinply Carbon diaphragm in a mid-range driver from Seas here.
Mm-hmm.
Lately, Perlism audio have been getting a lot of attention. This is their flagship tower, the S7T. Just the other day, I saw the Audioholics. They reviewed this and their new S4B bookshelf, and basically they said it was the best measuring and best sounding loudspeakers they have ever come across. So we're really happy what we have been part of achieving with our customers so far. But what's really interesting is what comes next. And that's when where the second generation Thinply Carbon diaphragm come in. Okay. Composite sound metamodal. And here we really use what we have touched upon before, how we can engineer the modal behavior. And to explain that, I also want to give that contrast between how it's done conventionally. And the traditional approach is really to reduce the negative effects of these undecided resonances. So in the hard cone way, like in aluminum cone, you try to make the stiff to move those resonances higher up in frequency. Typically, you end up with, the stiffer you make the cone, the worse that breakup is when it finally comes. Or you go 180 degrees the other way, you make the cone soft or add damping to reduce the amplitude of those modes. But it's like you're trying to reduce the symptoms. It's like if you have a pain in your back, you're eating painkillers. Well, the pain is still there. It might be smaller, but you also get other problems in your stomach, or can't think straight, or whatever. We go to the root cause to treat that. And there a composite sound metamodal comes in. So just like a metamaterial can be artificially structured to control light, or a metasurface can manipulate sound waves, composite sound metamodal manipulates resonances. And as we have already discussed, it's about optimizing that thickness and stiffness in different areas and different directions. So we remove the root cause of the problem. Okay. And how this can look like, if we again look on a conventional speaker console. So these are all identical. This is a mid-range driver. So this is an isotropic cone. It's in these simulations, it's based on an aluminum cone. Here, the modal behavior, it's sort of set. You get what you get. It cannot be changed in the cone itself. You can influence it in other ways, with the surround or other parts. Mm-hmm. In a composite sound metamodal, as said before, we can tailor the modal behavior. So these three drivers, again, are identical. The cones are identical in the way that they have the same geometry. For comparison reasons, we have made these cones equal in weight, but we have changed the stiffness in different places, the thickness in different places, so that you see that we get a completely different modal behavior. Mm-hmm. So this is actually, could call the first breakup modes, and that's that's also sort of up for discussion. What do we really mean with the first breakup? In an aluminum cone, I think it's quite clear what the first breakup is, because that's usually a huge peak. But in a composite sound meta model, we remove that first huge peak, and those resonances that come after that higher up in frequency, they are actually more difficult to pinpoint where they are, because I guess usually you say in an aluminum cone that the cone is pistonic until that first resonance breakup comes. There are things happening in the cone before. I think that the first breakup sort of indicates where you have substantial problems, you could say. So so that's this composite sound meta model technology. That's, I would say, our most powerful tool in order to achieve a well-damped controlled diaphragm behavior.
So a traditional cone manufacturer would say, yes, we have this breakup mode, but that's not a problem because we use a crossover and step the drivers up the frequency range. Do you have a position on why composite sound meta modal is still better in that regard?
That's borderline. Let's say if I should comment on that or not, because that's in a way outside of our, let's say, core competence, how you apply, let's say, our technology. What people usually say is that, some people definitely say that. Other people say that anytime you use a tool to sort of manipulate or let's say, try to reduce the symptoms of something without removing the cause, you're also creating other problems. And I'm actually not competent enough to judge exactly how, I actually
leave that up to the... no crossover is perfect, so the resonance is still there. I mean,
right.
It's not a brick wall. Nothing's a brick wall filter.
Right. I mean,
and just following up on that, do your customers find that they can use less number of drivers, like a two-way system instead of a three-way system, or use them for a wider bandwidth?
Yes, I think that's historically, when with the first generation, it was more about, our client, they had like a system. It was a two-way or a three-way, and they just replaced that same type of drivers, but just try to make them better. What we are working now in the project is how can we and our customers use our cone technology to allow them to design their speakers in more optimized, better ways. And that can be, exactly as you say, use the possibility with a wider bandwidth, for instance, and actually remove drivers. I mean, the full range application, I think it's perhaps the best, the most interesting application that we have with this technology.
I'm almost thinking of an analogy like with a car. If you take a set of Pirelli tires and put it on a Volkswagen, you might get some minor improvement, but if you build the car from the ground up to take advantage of the grip and etc. in those Pirellis, you'll get overall better performance. So that's kind of, you've started with phase one where you've introduced the cones and people stuck it into existing systems. They got so far, but if they can design the system from the ground up, knowing what they can adjust in the diaphragm design, then you get a much better system overall.
Yeah, that's a great analogy. I will use that. Thank you. So, and that really, is what this next slide is about, what we just touched upon, that, that the composite sound meta model really opens up new possibilities. We want that to be used to realize visions and solve problems that are, let's say, not solvable with conventional technology. So we see that it opens up for a unique level of design freedom, a new level of performance. As we mentioned before, here are just two examples of that we can actually engineer a frequency response. We can achieve a very wide range of pistonic motion. Actually, when we are beyond that pistonic range, we can still use the cone because we can control those resonances to much higher degree. Of course, we can make the cones even lighter, because what we do with composite sound metal model is that we put stiffness and material just in the places where it's needed the most. Meaning we remove material, we remove mass where it's not needed. So that enables us to really make ultra lightweight cones and diaphragms. And I would say all of this really opens up for geometrical freedom. In a conventional speaker cone, I think much the energy goes on to optimizing the geometry for stiffness, for instance. Here, we want to sort of shift the focus, because you don't need to design the geometry for stiffness so much more, so that you can instead optimizing the geometry for acoustic results, acoustic purposes. And in the end, I mean, what we just discussed, it opens up for new transducer solutions, new loudspeaker designs. So it's again about maximizing performance without compromises, without making sacrifices, and that's really what we mean. What I mentioned before, our mission: make it sound like you want it to sound. This is all what we mean about that. Just a few words also about the applications that we work with. Since we actually engineer the materials we use ourselves, and those materials, those texturing materials, have a huge flexibility. We can successfully use this in anything from big woofers to small micro diaphragms. Tweeters, mid-ranges, woofers, full ranges. I mentioned that's a very interesting application. Compression drivers, although that industry sort of had a dip now over the pandemic, but that's waking up again. Headphone diaphragms is also a very, very interesting area. Flat diaphragm micro speakers, we see also great possibilities. For instance, if you compare the properties, the performance we can achieve compared to aluminum, for instance, in a cell phone diaphragm. Radiating panels, that is BMR type of, DML type of panels, which is really about controlling, using modes and controlling those.
There'd be interesting stuff there in terms of with the BMRs, because actually Simon and I have spoke to Tectonic a couple of times, and they're using, I'd call it counterweights to get that cantilever mechanism we were talking about before. But perhaps something for you guys to patent, or probably you already do patent, the ability to control those points that the BMR otherwise uses counterbalances to achieve. Interesting. So that's what I had, let's say, prepared.
I'm kind of curious about. One thing you have, you showed some simulations. Have you been through a process of validating how accurately the simulation predicts the physical samples?
Yes. So I would say in all sample projects were ever made, and that's many. We always make simulations, and then we compare them to the actual results. And what we used to do, I actually have a slide on that, but what we used to do is make purely, let's say, mechanical simulations.
Yep.
We simulate the model behavior. We can simulate where does the breakup frequency come. Doing that, however, most people using console, for instance, they make axisymmetric simulations because they use aluminum cones or paper cones. Since we are varying the stiffness in different directions in different places, we are making a 3-dimensional cone. We need to simulate that in 3D. So we weren't able to simulate that acoustically. As I said, we can simulate where the breakup frequency comes, of course, the model behavior and the mass, but we had to do that with using simplified boundary conditions, because otherwise the simulations would just be too complex.
Yes.
But still, we got a fairly good let's say, agreement between our simulations and the actual measurements. Then in some cases, since we use simplified boundary conditions, there can be other parts that we sort of exclude from those simulations that have an effect on the performance. But what we're doing now is that we're really expanding our capabilities, and now we're able to simulate acoustically as well. And what we have seen is that, for instance, in console, it is possible to simulate 3D, composite anisotropic materials, but it has been a bit challenging to get that to work properly, but we're getting there now. So that's really, simulations are a very important part for our customers, because they want to be able to simulate to just, as a first step, just explore what would be the potential of our composite sound cones in their drivers and their loudspeakers. And then, of course, to optimize the cones and the drivers for our technology. And we also use it in that same way to optimize the cones for specific customers, but also to, drive the development of our technology forward. It's not like, if you have an aluminum cone, for instance, and then you come up with a new surface treatment and you increase the Young's modulus with 20%. You have a step and go from there. We sort of go from first generation to second generation, but we're not set there. Then we continually developing that. And using simulations is an extremely important part of that. Going back to your original question there, Simon. Yes, we have a fairly good agreement between simulation and actual results, and we are working on ways to be able to use simulations even better going forward.
So it's the kind of thing where it seems like that it's impossible to do a reverse calculation where you would say, okay, I want a flat frequency response and form that back into what diaphragm gives me that. You have to do it by sort of iteration and trial and error to kind of arrive at solutions. Basically, yes.
What we have done so far is, when we started, we had the idea that what would happen if we reinforce the cone in that place and increase the stiffness in that direction. And we basically tested that through simulations. And then we tested that and built that in specific cones and sent that to customers, and they tested that. So we have done that for many, many projects. So we have sort of built a library where we have, some basic constructions. We know that if we do it that way, it sort of has that effect. And then those basic constructions can, of course, be sort of tuned for specific geometries, depending on what the requirements are in a specific cone.
When you go back to the basic field small parameters, that part of the behavior is identical to a traditional speaker. Is that fair to say?
I would say so. I mean, we can of course, influence the mass and stuff like that, but basically that's the same, I would say.
Yep. And then for the most part, you can actually design the cone relatively independently of the rest of the system. That is to say, the size of the magnet and things like that.
Well, yeah. Well, usually sort of our client has perhaps a motor structure. So we have certain, let's say, boundaries that, that if we were speaking about a conventional cone, for instance, they have a specific inner diameter, and perhaps they have some range about the outer diameter or a certain height. In that, we can, of course, usually optimize the geometry. And with some customers now, we are actually starting from scratch. How can we, optimize the transducer from, the motor structure and everything? So there we're working more closely together with our customer in that respect.
Interesting.
Okay. And so this is all locked up with the patent. So the Thin-ply, is that something exclusive from TechStream and Composite Sound?
Well, there are some patents and there are some pending patents, but I mean, Thinply Carbon diaphragms, that's a category. Anyone can produce a Thinply Carbon. They can claim that they are doing a Thinply Carbon diaphragm.
Okay.
But of course, if they are to do that with a credibility, they should be able to, do it in a similar, or do it, to achieve the same type of performance. But that is not, let's say, protected in any way. And I suspect that there will be, followers, given the success we've had.
Yeah.
And that's why we're now putting, Composite Sound as a brand also on the map.
Okay.
And that's why we're also working so hard to be maintain our leading position in this respect.
So you're kind of a technology supplier is the goal?
Well, technology supplier, I mean, we supply, first, I mean, cones and diaphragms, but also let's say, a solutions provider. I mean, we have customer projects where, our customer does, large part of the engineering. We focus simply on the cone. They perhaps even provide us they want this geometry. In other cases, we help the customer optimize the geometry, for instance. I don't think we will ever be, designing loudspeakers for sure.
Right.
That's up to our customers. We might help our clients optimizing aspects of their transducer designs, for instance, to realize the full potential of our cone technology, given that the knowledge we have of that.
Right. Kind of back to how do you use these tires on this car kind of equation.
Yes.
Okay. And then just so locations now, offices in Sweden, have you spread out to sales somewhere in US, or how do you guys exist today?
So the headquarter is in Sweden. We have the cones are currently being produced in the US.
Okay.
But we are also building we have actually started already. We're building up a parallel production site in Sweden. So we will have an American-based production site. We'll have an European-based production site. If we will have something in Asia going forward, we have not really decided yet. Okay. And then we have, I mean, it's not, finding that right competence with people. It's not, just find that, within 30 kilometers from our head office. So, I mean, we have staff in Spain, Denmark, in the US. So we are actually, although we're a small company, we're a global company.
So you largely exist on Teams or Zoom as a
Very much on Teams.
Yeah, that's interesting. Is it's actually a collection of highly specialized skills to do this stuff, composite materials, acoustics, and things like that.
Yes. So I mean, where we were very, very strong from the beginning, it's of course on the composite side, on the composite simulation side. What we have now, besides really building on the general company infrastructure, what we have really added is, let's say, acoustic know-how, acoustic competence, acoustic simulation competence, for instance. We are building now a entirely new automated production line that will be up and running next year. So we're really accelerating the building of our company to take that next step to be let's say, also I mean, we are not going to be in the near future a mass market producer,
right.
But we are not going to be a small niche, exclusive company. We will be a high-end diaphragm producer, but also with solutions enabling the use and realization of our cones also in large volume applications. I mean, we have projects with several different projects with automotive, for instance, not to be commercially started in Q2 2023, but maybe in 2026.
Right.
So yeah.
Okay.
Interesting.
So the future sounds bright. So this all sounds like very good stuff. I think that's. You have any more questions, Simon, before we sign off?
No, perfect.
Okay.
Thanks.
So we'll put the information down below for everybody to find out more about composite sound. And of course, any comments or questions, either like it or hate it, please let us know. It's always good to get the feedback from everybody. So please like, subscribe, and do all that good stuff. And thank you, Martin, for joining us today. We really appreciate it.
Thank you. It was a true pleasure talking to you. I mean, speaking speaker cones, that's my favorite subject. So it was really a pleasure.
Okay. All right. So thanks, everybody. We'll talk to you next week.
Thank you.